Hey folks, welcome to another lesson, and we're kind of moving on to a new topic which is to do with the refraction of light. So we're going to state the definition of absolute refractive index. We're going to state Snell's law, and we're going to look briefly at how to analyze the experimental data to determine N of a material. Now, we would normally do this in class, and it's still worth doing because experimental data is examinable in the exam, so they may ask you to analyze some experimental data. Using analogy, otherwise explain how light changes path when undergoing refraction. So that could be an open-ended style question, basically. Okay, so to get you thinking, what causes rainbows, right? And hopefully don't tell me it is to do with unicorns pooing out rainbows, okay? You may remember from that 5 that rainbows were caused by a white light passing through a prism. And in fact, rainbows are caused by white light passing through raindrops, which gives you this kind of rainbow effect. Okay, so let's start with some definitions and see how this ties in with the rainbow a wee bit later on. So I'd like to write this down, and it simply says refraction is a change in velocity of a wave when it goes from one medium to another. Now, I want you to be really clear on this. This is the only definition that is guaranteed to give you full marks. You can come up with other definitions of refraction, but it may not be acceptable to SQA. So I would make sure you remember this. It's a change in velocity of a wave when it goes from one medium to another. And this is going to be really useful later on when we look at Snell's law and some other refraction effects. So a few things to remind you about. First of all, the speed of light in a vacuum is 3 times 10 to the 8 meters per second. And we also kind of assume that for light moving through air. For light moving through glass, the speed of light in glass is 2 times 10 to the 8 meters per second. And that's because glass is a much denser material than air or the vacuum of space, so it does tend to slow light down a little bit. One way to think about that is it's a bit like saying you walking through air compared to you walking through a really muddy field. And in the muddy field, it's probably slippery. You probably don't want to fall flat on your face in the mud, so you walk a lot slower. Now, to summarize that, the speed of light depends on the medium it's traveling through, and it depends on a factor called an optical density. So optical density is the measure of how light interacts with a medium. It is a technical term, but you don't need to remember it. I just want you to be aware of it, folks. So just to remind you of how refraction diagram works. So refractive index is one indicator of optical density. So remember our surface where the light ray hits it is called the interface. The light ray is always a straight line. It should be continuous, so there shouldn't be a break like that. Okay, but obviously I've been drawing this on PowerPoint. The light ray should also have an arrow to show which one it's going, so you know which way the light ray is actually traveling at. And we've got 2 angles that we're interested in. But to get to the angles, we need to define a few more things. And this thing is the normal, which is always 90 degrees to the interface. So if these arrows, these light rays went in here, the interface, the normal, sorry, would still be drawn where it is. And the normal is always 90 degrees. If you like, think of it as like a starting point for you to know where to measure your angles from, because your angles are always measured from the normal to the light ray. So from the normal to the light ray. So that's how we get these angles θ1 and θ2. We call θ1 the angle of incidence because an incident is where something happens. So that's where the light hits the interface. So that's where something happens. And the angle which comes out the other side is called the angle of refraction. Okay, now another definition for you, so please write this down, is the refractive index is given by the letter n, and it's simply the speed of light in the vacuum over the speed of light in the material. Now for air, because we've taken the speed of light in air to be the same as the speed of light in vacuum, using our definition here, it means we get a refractive index of 1. And notice there are no units. Refractive index is one of those few quantities that doesn't have any units, so don't get caught out by that. N is usually greater than 1 and never negative. Right, so a follow on from the refractive index definition is this. When light is refracted as it travels from air to glass, then the angle of incidence will always be the angle greater than the angle of refraction. So notice in my diagram how this angle here, the angle of incidence, is actually bigger than the angle of refraction. And that's always true when light goes from air into glass. The opposite is also true. If it was going from glass into air, then the angle in the glass would be smaller than the angle outside of the glass. Okay, now this is where we do the experiment, so I'm going to just sit through this fairly quickly, but all it is that you would be measuring different angles of incidences and the corresponding different angle of refraction, and then you take sine of the angle of refraction and the sine of the angle of incidence, and you divide the two, and then you hopefully should get some interesting results. Now, in fact, what you should get is if you plot sine theta 1 on the y-axis and sine theta 2 on the x-axis, you should get a lovely straight line like this, which, if you remember, means that it's a proportional relationship. And if we work out the gradient, it should be a constant because it's a straight line. And in fact, if we work out the gradient, i.e. if we take y over x, because remember that's a general equation for a straight line, then correspondingly, that's the same as sine theta 1 divided by sine theta 2. We can find the actual refractive index of the material. So experimentally, we have a method for determining the refractive index of a material. Okay, now there's a few things you need to know about this. Number one refers to the angle and refractive index in air or medium 1. Okay, so air is always taken to be theta 1. 2 is always taken to be the angle in glass or medium 2. And this will become more obvious when we come to do some worked examples. So here, when a ray passes from light into a glass block, the angle of incidence is 45 degrees, angle of refraction is 28 degrees. What is the refractive index of the glass? So feel free to try this question yourself. It's actually fairly straightforward. I'll take you through it just now. So remember, our equation is sine theta 1 over sine theta 2. And remember, I said to you that theta 1 is the angle in the air. So that means it's 45 degrees. And theta 2 is the angle in the glass. So that's this angle here. So we plug it in, calculate it using our calculator, and we get the refractive index is 1.5. So fairly straightforward to do that. We can, of course, make the problems a bit more trickier. Okay, so this is the final slide, and it's basically an analogy for us to explain why having a changing speed leads to refraction. Now, this came up as an open-ended question a couple of years ago, so it might come back in some form, so it's worth knowing this explanation. So the analogy is that imagine a car is driving from the road into a muddy field. So you can see there's my car going from the road onto a muddy field. In a muddy field, it slows down as there's more friction. If it enters the field at an angle, then the front tyres will hit the mud at different times. So you can see in my diagram, this tyre here is going to hit the mud before the tyre on the opposite side. So tyre 1 hits the mud first and will move more slowly than tyre 2. This causes the car to turn towards the normal or to turn inwards. So that's how we explain the refraction effect. Now we can do the opposite and say, well, what happens when the car goes from mud onto the road? Well, when the car leaves the mud for the road, tyre 1 hits the road before tyre 2. So again, it's kind of like the going in at an angle. And this causes the car to turn away from the normal because now tyre 1 is on the road, so it's got less friction, so it's more likely to turn the car in again away from the normal. Now, I'm going to leave you one question. what happens if the car didn't go at an angle but actually travelled in a straight line like this? Okay, exactly 90 degrees to both interfaces. Would there be any refraction? Okay, have a think about it. We'll talk about it next time.